A cold, thin cloud hangs in a quiet corner of the galaxy spread across light years of darkness, almost empty and yet filled with the seeds of worlds. It drifts in slow motion around the center of the Milky Way, a veil of gas and dust so faint that from far away it would seem like nothing at all. Inside this cloud, atoms remember earlier generations of stars. They carry the ashes of long dead giants, fragments of heavier elements forged in explosions and scattered into space. Iron, carbon, oxygen, and grains of silicate dust float together in a chilled stillness only a few degrees above absolute zero. For ages the cloud appears unchanged, a tranquil shape in the dark, but gravity is always at work. Tiny clumps of slightly denser material pull a little harder on their surroundings. Over millions of years, these gentle tugs add up. The cloud begins to feel its own weight. Motions that once canceled each other start to fall into a slow inward drift. Somewhere near the center of the cloud, density grows just enough for a pattern to form. A region becomes marginally thicker, still diffuse by any human measure, yet more massive than the wisps around it. As it draws in more material, it also starts to spin. The original rotation of the cloud, perhaps almost imperceptible at first, is preserved and magnified as everything falls inward. What was once a vague and formless patch of gas now gathers into a flattened rotating structure. A young forming star takes shape at the middle, wrapped in a broad disk of swirling dust and gas. The scene remains quiet when viewed on the immense timescale of star formation. Light builds very slowly. Temperature climbs at the core as the mass grows, and atoms are squeezed closer together. The central region glows first in invisible wavelengths, a warm embryo of a future star still hidden within the shroud. Around it the disk circles in a patient, ordered motion, with inner regions completing laps far more quickly than the distant rim. Inside this protoplanetary disk, dust grains collide with one another. At first, the collisions are gentle, glancing contacts between tiny particles that cling through electrostatic forces. They form fragile clusters like delicate snowflakes of rock and ice. Many of these clusters break apart again, ground down by turbulence and repeated impacts, yet a fraction survive. Over time, the successful clumps grow larger and heavier. They begin to settle toward the midplane of the disk, forming a thin, dense layer within the gas. In this crowded sheet, collisions become more frequent. Pebble-sized bodies emerge, pebbles become boulders, and boulders give rise to kilometer-scale planetesimals, embryonic building blocks of future planets. Each new body carries its own small gravity, allowing it to attract additional material and carve subtle gaps and spiral patterns in the surrounding disk. The young star at the center now shines more steadily. Nuclear fusion begins converting hydrogen into helium and releasing a steady flow of energy. Stellar winds push outward, clearing lighter gas from the inner regions of the disk and shaping the structure that remains. The forming planets are left embedded in this changing environment, locked into orbits that circle the new sun, their paths defined by the distribution of mass and the graceful balance between gravity and motion. Closer to the star, temperatures remain high enough to drive away volatile ices. Rocky worlds assemble from silicates and metals that can withstand the heat. Farther out, where the sun is a softer glow and the cold preserves light elements, icy grains accumulate in abundance, helping giant planets to swell around cores of rock and ice. Even farther still, beyond an invisible frost line, countless frozen fragments drift in the dim light, waiting as the raw material for distant comets and outer belts. The birth of the solar system is not a single moment, but a long, overlapping sequence of processes. Clouds collapse as disks flatten. Dust gathers as planets coalesce. Impacts are frequent and violent on a human scale, yet from the perspective of cosmic time, they resemble gentle reshaping of a slow-moving sculpture. Craters, tilted axes, and captured moons that will later puzzle observers all trace back to this era of assembly. The overall picture seems orderly, a family of worlds forming from a shared disk around a single star, but small variations in density, temperature, and timing introduce endless variety. A slight difference in where one clump forms or when another is scattered can change the size, composition, and orbit of a future planet. In some regions, growth halts early, leaving behind only fragments. In others, runaway accumulation creates bodies that dominate their neighborhoods and remodel the paths of smaller objects. As the disk thins and clears, what remains is a newborn solar system bathed in the steady light of a young sun. The planets continue to adjust their positions through lingering interactions, trading angular momentum and nudging each other into more stable paths. Around them, leftover debris settles into belts and clouds, reservoirs of ice and rock that preserve the memory of the system's earliest days. In this seemingly calm and finished arrangement, faint imprints of its turbulent origin remain waiting to be read in subtle orbital quirks and chemical clues. The quiet sky that will one day look peaceful from the surface of a small blue world is already filled with the outcomes of hidden choices made during this slow, unseen birth. The sun stands at the center of the solar system as a constant glowing presence, its light washing over every orbit and surface with a steadiness that seems almost absolute. From a quiet distance it appears unchanging, a smooth disk of soft light that rises and sets with dependable rhythm. Hidden within that apparent stability are slow pulses and gentle variations that unfold over stretches of time far longer than a single human life. Deep inside the sun, far below the bright surface, pressure and temperature climb to extremes where hydrogen atoms are pressed together. In that compact core, nuclear fusion releases energy that begins a long, patient journey outward. Photons scatter through dense layers of gas, their paths twisted into a random walk that can take hundreds of thousands of years to reach the visible surface. By the time this energy emerges as sunlight, any trace of its chaotic path has been smoothed into a uniform soft glow. The sun rotates, but not as a solid object. Its equator completes a turn in roughly 1 month, while higher latitudes move more slowly. This differential rotation stirs and winds the magnetic field, drawing invisible lines of force into loops and knots. On the surface, these buried tensions appear as dark sunspots, slightly cooler regions, where the magnetic field arches out of the gas and briefly holds back the upward flow of heat. To an observer watching over many years, the number and size of these spots rise and fall in a repeating pattern lasting about 11 years. During the peak of this cycle, the sun shows more blemishes, more flares, and more sudden brightenings in higher energy light. During the quiet years, its face can appear almost spotless for long stretches of time. Yet even in its most active phase, the overall output of light changes by only a small fraction, just enough to whisper a soft influence into the climates of orbiting worlds. Sensitive instruments on satellites measure these tiny shifts as a slowly varying solar constant, a value that is almost but not quite unchanged. Spacecraft that watch the sun continuously record the rise and fall of active regions, the eruption of prominences, and the rhythm of large ejections that send clouds of charged particles streaming into space. These events follow the same broad cycle, clustering around times when the magnetic field is most twisted and complex. The sun's magnetic poles gradually weaken, reverse, and rebuild in the opposite orientation, completing a larger magnetic cycle that spans roughly 22 years. To the planets, these slow changes act as a kind of heartbeat, modulating the stream of particles known as the solar wind that flows outward in all directions. When the sun is more active, the solar wind becomes denser and more turbulent. It carves a slightly larger bubble in the thin gas between the stars, stretching the heliosphere farther out. Charged particles from the sun interact with planetary magnetic fields in upper atmospheres, forming auroras near the poles and altering the flow of energy through high-altitude layers of air. On Earth, these effects leave gentle traces in the upper atmosphere. The sun also shows deeper variations that unfold over centuries rather than decades. Historical observations record periods when sunspots nearly vanish for many years. During one such era in the 17th century, now called the Maunder minimum, parts of Earth experience cooler conditions that some records describe as a little ice age. The link between long-term solar quiet phases and climate shifts remains an open question, explored through models and proxy data, but not yet fully resolved. Even in the present day, solar physicists continue to refine their understanding of how magnetic fields emerge from the sun's interior and why the cycle sometimes weakens or strengthens in ways that are not fully predicted. Waves ringing through the sun like sound in a resonant sphere reveal flows and layers beneath the surface that hint at large-scale currents of plasma carrying magnetic fields around the star. These internal patterns may control the timing and intensity of future cycles, but the exact mechanisms are still the subject of careful observation and quiet debate. Over even longer spans of time, the sun brightens very gradually as helium ash accumulates in its core, altering the balance of pressure and temperature. Calculations suggest that when the solar system is young, the sun shines less brightly than it does now, yet ancient rocks on Earth point to the presence of liquid water under a sky that receives this fainter light. This faint young sun paradox raises another puzzle, inviting ideas about greenhouse gases and atmospheric feedbacks that might have compensated for the lower energy. Seen on any human timescale, the sun remains a model of reliability, rising and setting with almost perfect regularity, illuminating the planets with an unfailing stream of light and warmth. Beneath that calm appearance, however, lie layers of slow processes, cyclic rearrangements, and gradual trends that ripple outward through the entire solar system. Each small fluctuation in magnetism or brightness is softened by distance and time, yet together they weave a subtle pattern into the histories of planets, moons, and atmospheres. The sun's slow, steady heartbeat is more than an image. It is a real and measurable rhythm, felt in the chemistry of the upper air, in the tails of comets, in the boundaries of the heliosphere, and in the long memory of climate records. Somewhere between the apparent constancy of everyday sunlight and the deep time over which stars evolve, an intricate ongoing story continues to unfold, inviting a calm attention to this quiet pulse at the center of the solar system. In the quiet expanse around the sun, the planets move along their paths with such regularity that their motion can be treated as a vast natural clock. Each world follows an orbit shaped by the balance between the pull of gravity and the tendency of motion to continue in a straight line. The result is a series of long curved tracks traced in near silence through space, repeated over and over again with almost perfect consistency. From the surface of one small planet, this motion appears as the cycle of days, months, and years, but seen from above the plane of the solar system, it becomes a graceful dance of ellipses nested around a common center. The inner planets circle the sun more quickly, their years lasting only a small fraction of the time taken by the distant giants. Mercury completes many laps in the span of a single Earth year. while Neptune requires more than a human lifetime to trace a single loop. These differences arise directly from the strength of gravity at each distance. Closer orbits feel a stronger pull and must move faster to remain balanced. Farther orbits move more slowly, their gentle arcs stretching out over immense periods of time. The pattern is simple enough that early astronomers could predict planetary positions using only mathematics and careful records of past motion, long before they understood the deep source of gravity itself. Over centuries, this predictability created an impression of perfect order, as if the solar system were a flawless celestial machine. Yet even in this clockwork picture, small irregularities emerged. When Jupiter and Saturn pass specific points in their paths, their combined pull tugs on other bodies, altering their orbits by tiny amounts. Asteroids that circle the Sun at certain distances find their paths repeatedly disturb their periods, matching simple fractions of the orbital times of larger planets. These resonances gradually clear gaps in the asteroid belt, carving out regions where long-term stability is difficult. In other places, resonance locks bodies into enduring patterns, allowing them to share orbits without collisions. The regularity of these patterns and the empty spaces they create hints at a structure more intricate than a simple set of independent ellipses. The orbits communicate with one another through gravity exchanging angular momentum in slow, cumulative ways. Even the nearly circular path of Earth is subject to gentle changes over tens of thousands of years as the tilt of its axis, the shape of its orbit, and the slow wobble of its orientation evolve in response to the pulls of other bodies. These Milankovitch cycles leave their imprint in climate records, connecting subtle shifts in the geometry of the orbit to the rhythm of ice ages and interglacial warm periods. While the clockwork continues to tick with remarkable precision, its gears drift, creating long-term patterns that are only visible when many cycles are combined. Smaller bodies offer another window into the layered regularity of motion. Comets from the Kuiper belt and the distant Oort cloud fall inward along elongated paths, their orbits carrying them close to the Sun and back out again over periods that can span centuries. Some of these orbits are nudged into resonance with planets, turning a one-time visitor into a returning presence with a fixed period. Others are gradually altered until they become almost circular, transformed from icy wanderers into more settled members of the planetary family. The continual interplay of gravitational tugs keeps the solar system both ordered and quietly restless. Spacecraft sent from Earth trace their own paths through this moving framework. Mission planners calculate trajectories that borrow energy from planetary motion, using gravity assists to bend flight paths and change speeds without expending large amounts of fuel. A probe passing behind a planet in its orbit can gain speed, while one that passes ahead can lose it. When a spacecraft changes course through a planetary flyby, the planet itself also shifts by a tiny amount, though the difference is too small to notice. Every push has a corresponding pull, and every change in one orbit is balanced by changes shared through the whole. On the scale of billions of years, even minor exchanges accumulate. Simulations that follow the planets forward and backward in time show that their orbits, while largely stable, can wander within narrow bounds. The inner planets in particular lie near a threshold of chaotic behavior, where extremely small differences in starting conditions can lead to different outcomes over very long periods. This sensitivity does not destroy the clock-like nature of the system on human or even geological timescales, but it introduces a quiet uncertainty into its distant future. The solar system of today is one particular arrangement selected from many possibilities, that could have arisen from its early conditions. The regular motion of the planets thus becomes both a source of comfort and a reminder of deeper complexity. Each sunrise and season is anchored in the dependable progression of Earth around the Sun, while less visible interactions rearrange the details of orbits in ways that only precise measurement can reveal. The great cosmic clock keeps time, but its hands do not follow tracks cut once and for all. Instead, they move along paths that are constantly and subtly rewritten by the mutual pull of every body on every other, leaving patterns of resonance gaps and long-term cycles as delicate marks of this ongoing gravitational conversation. In the calm and repetitive turning of these orbits, the entire history and future of planetary climates, impacts, and alignments are quietly encoded, waiting to be inferred from the patient study of their motion. Mercury circles close to the Sun, a small, dense world bathed in intense light and shadow, its surface turning slowly beneath a sky that never truly darkens. From orbit it appears as a heavily cratered sphere, scarred like the Moon, but with its own distinct character, a patchwork of old basins, cliffs, and smooth plains. The planet is locked in a curious relationship with its star, rotating 3 times for every 2 orbits, so that a single day from one noon to the next stretches across long weeks. This resonance creates a strange pattern of heating and cooling, where some regions linger in sunlight for extended periods, while others endure prolonged cold. The contrast between blistering dayside temperatures and freezing nightside conditions is extreme, yet thin wisps of material cling in small sheltered pockets, hinting at processes still quietly active. For much of history, Mercury remains a difficult target for observation. Its proximity to the Sun keeps it low on the horizon, visible only at dawn or dusk, and distorted by the atmosphere of Earth. Early measurements of its orbit show a slight discrepancy between prediction and reality. The point of closest approach to the Sun, called perihelion, advances over time in a way that classical calculations cannot fully explain. Most of this motion can be accounted for by the gravitational pull of other planets, but a small excess remains a stubborn anomaly that resists tidy solutions. Astronomers test various possibilities, wondering if an unseen inner planet or a belt of dust might be exerting an additional pull. These ideas eventually give way to a more profound revision. When the theory of general relativity proposes that gravity arises from the curvature of space-time itself, one of its first precise tests lies in the orbit of Mercury. Using the new equations, the unexplained excess in the precession of perihelion is reproduced with remarkable accuracy. The planet's delicate shifting path becomes one of the earliest confirmations that space and time are not rigid backdrops, but active participants in motion. In this way, a small world close to the Sun quietly helps reveal a deeper structure of reality. Spacecraft sent to Mercury add further layers of mystery and detail. The Mariner and Messenger missions, followed later by the Bepi-Colombo mission from the European Space Agency and the Japan Aerospace Exploration Agency, map the planet's surface, measure its gravity and magnetic field, and sample particles in its environment. They find that Mercury, despite its modest size, retains a global magnetic field, something unexpected for a body that should have cooled quickly. This field carves out a miniature magnetosphere, a protective bubble that deflects some of the solar wind, but also channels charged particles toward the surface. Observations reveal a surprisingly dynamic exosphere, a thin envelope of atoms released by impact solar radiation and chemical reactions. Sodium, potassium, and other elements appear in faint glows, forming a ghostly, ever-changing halo around the planet. Certain regions near the poles harbor permanently shadowed craters where sunlight never reaches the floor. Radar reflections from Earth and data from orbiting spacecraft indicate the presence of deposits with properties matching water ice mixed with dark insulating material. The idea of ice surviving on a world so close to the sun seems at first counterintuitive, yet the combination of deep shadow and vacuum allows volatile compounds to persist in cold traps for millions of years. These polar reserves raise questions about delivery mechanisms, pointing to comets and asteroids as likely sources, and about how long such materials have been present. The surface of Mercury also bears long curved cliffs called lobate scarps features that cut across craters and plains alike. These structures suggest that the entire planet has contracted slightly as its interior cooled, wrinkling the crust like a drying fruit. The amount of shrinkage appears larger than early models predict, hinting at a more complex thermal history. Inside a large metallic core occupies a significant fraction of the planet's volume, much bigger in proportion than the cores of other terrestrial worlds. This oversized core contributes to Mercury's high density and may still be partly molten, driving the magnetic dynamo that generates the global field. How such a configuration arises remains a subject of ongoing investigation. One family of ideas proposes that early in its history, Mercury suffers a giant impact that strips away much of its original mantle, leaving a metal-rich remnant. Another suggests that intense solar heating during formation removes lighter elements more efficiently from the innermost region of the disk. Each scenario carries testable predictions about composition and structure, yet none has closed the case. Measurements of surface abundances reveal unexpected levels of volatile elements, complicating any picture that relies solely on extreme stripping or evaporation. Mercury thus stands as a compact catalog of puzzles. Its orbital resonance, confirmed precession, magnetic field, oversized core, scarred and shrinking crust, polar ice, and restless exosphere weave together into a story where each apparent solution opens additional questions. The planet's proximity to the sun, once a barrier to observation, turns out to be a key to understanding conditions in the inner regions of planetary systems. As missions refine maps of its gravity and topography, subtle variations hint at buried structures and past flows, inviting deeper models of how metal and rock separate, cool, and move within such a world. In the calm sweep of its orbit, Mercury carries the memory of forces that extend from the scale of its spinning core to the curvature of space-time itself, a small, bright point near the sun that gently unsettles any assumption that the smallest planet must also be the simplest. Venus shines in the twilight sky as a steady, pale beacon, its light softened by thick clouds that hide the surface from direct view. From far away, it seems gentle, a near twin to Earth in size and position, orbiting in a slightly smaller path closer to the sun. Yet beneath this bright veil lies a world that has turned backward and overheated, a planet whose present state hints at a long and intricate past. Venus rotates in the opposite direction to most planets in the solar system, so that for any imagined observer on the surface, the sun would appear to rise in the west and set in the east. The spin is also extremely slow, with one full rotation taking longer than the time needed to complete a year-long orbit around the sun. This retrograde and languid motion suggests a history shaped by powerful events or long tidal interactions, but the precise sequence remains uncertain. Some ideas point to an early giant impact that altered the spin, others to a gradual breaking and reversal as the dense atmosphere and the sun exchanged angular momentum with the solid planet over immense spans of time. Above the hidden surface stretches an atmosphere so thick that it behaves almost like an ocean of air. Carbon dioxide makes up most of this envelope, with traces of nitrogen and sulfur compounds woven through it. At the surface, the pressure reaches levels many tens of times higher than at sea level on Earth, comparable to conditions found deep beneath the oceans of the homeworld. Temperatures remain high enough to melt lead, a result of an intense greenhouse effect in which heat from the sun becomes trapped by the dense blanket of gas and scattered many times before slowly escaping back into space. High overhead, bright clouds composed largely of sulfuric acid droplets swirl in continuous bands driven by fierce winds. These upper layers race around the planet in a pattern of superrotation, completing a circuit in only a few Earth days, even while the solid body beneath turns almost imperceptibly. The contrast between the sluggish planet and the rapid atmosphere intrigues dynamicists, who seek to understand how waves, solar heating, and planetary rotation combine to sustain such a persistent circulation. The clouds reflect most of the incoming sunlight, which is why Venus appears so bright in the sky, yet enough energy filters through to keep the lower atmosphere and surface locked in a nearly uniform oven-like state. Spacecraft have gradually peeled back the obscuring veil. Early missions measured the heat radiating from the planet and confirmed the harsh surface conditions suggested by remote sensing. Landers that descended through the crushing atmosphere returned brief images and data before succumbing to the pressure and temperature, proving that the landscape is rocky, fractured, and littered with volcanic forms under a heavy sky. Later orbiters used radar to map the terrain through the clouds, revealing broad plains of solidified lava, towering shield volcanoes, and complex highland regions known as tesserae. These areas of intersecting ridges and valleys appear heavily deformed and ancient, perhaps preserving a record of an earlier geological era when the crust behaved differently from the present day. The overall lack of large numbers of impact craters compared to the expected rate suggests that the surface has been extensively resurfaced in the relatively recent geological past, possibly through widespread volcanic activity that covered older terrain with new layers of rock. Whether this resurfacing occurred in a single global episode or through continuous but uneven eruptions over time remains an open question, and each possibility implies a different story for how heat escapes from the deep interior. Clues also hint that Venus may once have possessed a more temperate climate. Models that trace the evolution of the star in the atmosphere indicate that for a long period earlier in its history, the planet could have maintained liquid water on its surface, perhaps in shallow seas or oceans, where clouds, rain, and rock interacted in ways broadly similar to those on young Earth. Ratios of hydrogen isotopes in the current atmosphere, with a higher proportion of heavy deuterium compared to ordinary hydrogen, suggests that large amounts of water have been lost to space. In this scenario, increasing solar brightness and greenhouse feedbacks gradually evaporate the oceans, allowing water vapor in the upper atmosphere to be broken apart by ultraviolet light, with hydrogen escaping and heavier particles left behind. If this path is correct, Venus may represent a former Earth-like world that crossed a threshold and entered a new, more hostile state that is difficult to reverse, turning from potential ocean planet to global furnace in a slow but decisive transition. The idea that seas may once have existed beneath the clouds, now replaced by crushing heat and pressure, adds a layer of quiet unease to the bright point of light that seems so calm from a distance. High above the clouds, the region where the atmosphere meets the solar wind forms a restless boundary. Unlike Earth, Venus lacks a strong intrinsic magnetic field generated by a rotating metallic core, so the flow of charged particles from the sun interacts directly with the upper atmosphere. An induced magnetosphere shaped by currents and ionized gas offers partial shielding, while also helping to strip away atmospheric particles over long periods, especially from the night side where a faint tail of escaping material extends into space. Measurements from orbiters trace these flows and waves, revealing a system that responds to changes in solar activity and adding another slow process to the planet-sized experiment of climate and escape. Earth travels around the sun as a modest blue and white world where land, ocean, and air combine into a delicate balance that supports liquid water on the surface. From space, the planet appears calm, its swirls of cloud drifting over continents and seas in patterns that seem slow and repetitive. Beneath this apparent stability lies a mesh of linked systems, each adjusting quietly to changes in the others and holding conditions within narrow bounds over very long periods of time. The distance from the sun sets the basic level of incoming energy. At this orbit, sunlight arrives with an intensity that would freeze the oceans if the air were too thin, or bake the surface dry if the atmosphere trapped too much heat. Instead, a mixture of gases, including nitrogen, oxygen, water vapor, and carbon dioxide, forms a blanket that allows visible light to reach the ground while slowing the escape of infrared radiation back into space. This greenhouse effect raises the average surface temperature enough for liquid water to persist in vast amounts, turning the planet into a world of lakes, rivers, and oceans. The angle between Earth's spin axis and the plane of its orbit gives rise to seasons. At any given time, one hemisphere leans slightly toward the sun while the other leans away, changing the height of the midday sun and the length of the day. This tilt, a little more than 23 degrees, does not remain fixed. Over tens of thousands of years, it oscillates within a small range, altering the contrast between seasons. Small variations in the shape of the orbit and a slow wobble in the orientation of the axis add further shifts. Together, these orbital variations change the distribution of sunlight across latitudes and seasons in subtle ways. Geological records preserved in ice cores, ocean sediments, and ancient shorelines reveal that these cycles line up with the timing of ice ages and milder interglacial periods. When northern summers become slightly cooler because of orbital geometry, ice sheets are more likely to grow and persist. When summers grow slightly warmer, ice retreats. The link between small changes in sunlight and large changes in climate depends on feedbacks involving snow ice clouds and greenhouse gases, feedbacks that amplify the original orbital nudges into more dramatic shifts. In this way, the planet's long-term climate carries the imprint of its slowly changing path and tilt, turning celestial mechanics into a quiet metronome for glacial rhythms. Earth's surface and interior also take part in the balance. Plate tectonics slowly rearrange continents, open and close ocean basins, and build mountain ranges. As rocks are uplifted, they are exposed to weathering, a process that draws carbon dioxide from the atmosphere and locks it into minerals. Volcanic activity returns some of this carbon to the air, forming a feedback between atmospheric carbon dioxide temperature and weathering that acts as a planetary thermostat. The oceans serve as both memory and mediator. Currents carry heat from equatorial regions toward the poles and return colder water at depth, smoothing temperature contrasts. Layers within the sea absorb and release heat over years and centuries, storing the imprint of past conditions, while the upper ocean exchanges gases with the atmosphere. Because these processes operate at different speeds, the climate system never snaps into a new state. It drifts, overshoots, and relaxes, tracing loops of adjustment that can span many generations. Even the length of the day participates in the quiet evolution of conditions. Tidal interactions between Earth and its moon transfer angular momentum from the spin of the planet to the orbit of the satellite. Over millions of years, the rotation of Earth gradually slows while the moon recedes ever farther away. Fossil corals record that days were once shorter and years contained more of them. The present balance between rotation, tilt, and solar heating is only one frame in a longer film. Within the core of Earth, liquid metal moves in complex flows that generate a global magnetic field. This field shields the atmosphere from much of the charged particle radiation streaming from the sun and from space, reducing the rate at which lighter gases escape. The magnetic field reverses polarity irregularly over time, flipping north and south in events that leave distinct signatures in cooling volcanic rocks on the seafloor. The existence of this protective cocoon, sustained by deep motions of molten metal, adds another component to the planet-layered stability. Taken together, these factors paint Earth as a world maintained by a tapestry of slow adjustments. Orbital cycles modulate sunlight, atmospheric composition controls how much heat remains, oceans transport energy and chemicals, rocks and interior dynamics set the pace of long-term feedbacks, magnetic fields guard the outer boundary against erosion by space weather. None of these systems is perfectly steady, and each shows episodes of more rapid change when viewed up close. Yet across hundreds of millions of years, the overall pattern remains one in which liquid water moderate temperatures and a thick atmosphere persist. Within that relatively narrow window, continents drift, climates swing, and life evolves. The mystery lies in how finely tuned this balance appears when compared with the possible variations that physics allows. The same laws that could have produced a frozen or scorched planet instead give rise to a temperate one whose properties shift just enough to remain dynamic without often crossing into lasting extremes. Understanding how chance feedback and deep time have combined to sustain this state remains an open question that continues to draw careful attention as Earth carries on in its orbit, adjusting in ways that are mostly too slow to notice from one day to the next. The moon circles Earth as a quiet companion, always presenting the same face toward the planet, its mottled surface marked by pale highlands and darker plains that trace a history far older than any visible on the ground below. In the night sky it appears serene and familiar, gliding through phases that repeat with steady rhythm, yet close inspection reveals a complex record of impacts and interior changes that together tell a story of origin and evolution still not fully resolved. The locked rotation that keeps one hemisphere forever turned toward Earth arises from tides raised in the moon itself. Early in its history, the moon almost certainly rotates more quickly, but the pull of Earth raises bulges in its solid body that lag slightly behind the line connecting their centers. As the moon turns, these misaligned bulges experience drag that gradually slows the rotation and transfers angular momentum to the orbit. Over time, the spin period lengthens until it matches the orbital period, a state known as synchronous rotation, after which the same side always faces the planet. The visible hemisphere, though always turned toward Earth, is not entirely fixed. A gentle rocking motion called libration allows observers to see a little beyond the average edge over each cycle, revealing that the far side is markedly different. While the near side hosts broad dark plains formed by ancient volcanic eruptions that filled huge impact basins with smooth lava, the far side is dominated by bright, heavily cratered highlands with far fewer such plains. This pronounced asymmetry raises questions about differences in crust thickness, heat flow, and impact history. Measurements from orbiting missions indicate that the crust on the far side is generally thicker, which may have inhibited the rise of magma to the surface there, leaving it more heavily scarred and less resurfaced. The origin of this thickness contrast remains uncertain, with ideas ranging from uneven early heating by a still glowing Earth to the collision and merger of a smaller companion moon that coated one hemisphere with extra material. The formation of the moon itself stands as one of the central puzzles in planetary science. Rocks returned by human explorers and robotic landers reveal that lunar samples share many chemical and isotopic similarities with Earth mantle material, particularly in the ratios of oxygen isotopes. At the same time, the moon is depleted in volatile elements and enriched in more refractory ones, a pattern that points toward a high-temperature origin. The leading framework proposes that a Mars-sized body collides with the young Earth in a grazing impact, ejecting a mixture of mantle material and impactor debris into orbit. This debris forms a hot, dense disk that later coalesces into the moon. Simulations of such a giant impact can reproduce many observed properties, including the large size of the moon relative to Earth and the angular momentum of the system. However, the very close match between some isotopic signatures in Earth and Moon remains challenging to explain, fully encouraging refinements such as more thorough mixing in a shared vapor envelope or alternate collision geometries. Each improvement brings models closer to the measurements, yet leaves room for uncertainty, and the Moon continues to serve as a natural laboratory for testing ideas about how planets grow through large collisions and how debris disks turn into satellites. The surface preserves a detailed record of impacts that extends back over billions of years. Large basins with multiple rings trace catastrophic events in the early solar system, when leftover planetesimals and fragments still roam in great numbers. The density and layering of craters across different terrains allow researchers to reconstruct a timeline of bombardment, including a possible concentration of impacts in a period sometimes called the late heavy bombardment. Whether this episode represents a true spike in collision rates or a more complex interplay of surface renewal and impact flux remains under discussion. Regardless of exact timing, the moon crust archives a history of blows that would have affected all inner planets, including Earth, where erosion and plate motion have erased much of the direct evidence. The moon also exerts its own influence on Earth, raising tides in the oceans and in the solid body of the planet. As tidal friction slows Earth rotation and transfers angular momentum outward, the moon slowly recedes. Laser ranging experiments that bounce light off reflectors placed on the surface measure this drift with remarkable precision, finding that the distance grows by a few centimeters per year. Extrapolated backward, this suggests that in the distant past the moon orbits closer and appears larger in the sky, while days on Earth are shorter. Sedimentary layers on the planet preserve hints of these ancient rhythms, with patterns consistent with more frequent tides and faster rotation. The coupled evolution of the two bodies entwines their histories, making the current configuration only one moment in a longer exchange. Even today, the moon continues to shape subtle details of Earth climate and rotation through its gravitational pull. In return, observations of the moon refine understanding of broader questions about planetary formation, interior structure, and the history of the inner solar system. Beneath its familiar appearance lies a network of unresolved issues that keep this quiet companion at the center of ongoing exploration. From orbiters mapping its poles and crust in finer detail to missions that target regions which may hold untouched records of early conditions. The moon, steady in the sky and synchronous in its spin, remains both a comforting presence and a source of open questions, a nearby archive of events that reach far beyond its own small sphere. Mars circles the sun as a quiet, rust-colored world smaller than Earth and wrapped in a thin, cold atmosphere. From orbit, its surface appears as a broad expanse of deserts, canyons, and impact basins shaded in reds, browns, and pale dust. Dry dunes curl across crater floors, and fine dust mists the air in storms that can grow to cover much of the planet. At first glance, it seems like a long dead landscape of frozen desert shaped only by wind and impact. Yet when the shapes of its valleys and plains are examined in detail, another story begins to emerge, one that hints at flowing water and a climate that once differed sharply from the present. Networks of branching valleys cut into ancient highlands, converging into larger channels in patterns that closely resemble river systems on Earth. Some channels appear carved into the terrain over long timescales, winding back and forth in gentle curves. Others look abrupt, as though enormous floods once burst from underground reservoirs and rushed across the surface before fading away. At the ends of certain valleys, fan-shaped deposits spread into basins, their layered forms suggesting deltas built where water once slowed and deposited sediment. Inside craters, flat plains at consistent levels look like the floors of ancient lakes. Orbital instruments that measure subtle differences in mineral signatures add support to this picture. Clays and sulfates, which commonly form in the presence of liquid water, are found in and around these basins and valley systems. Their distribution suggests that water once stood in place long enough to interact with rock, altering its chemistry. Some regions show minerals that point to neutral or mildly alkaline conditions, while others indicate more acidic environments, implying a range of water chemistries over time. Together, shapes and minerals trace a planet that likely hosted long-lived lakes, transient seas, and perhaps even a global ocean in its northern lowlands. Rovers that traverse the ground add close-up detail to this broad view. They photograph rounded pebbles and layered sedimentary rocks, record cross-bedding, and tiny ripples frozen in stone, and analyze the composition of drilled samples. Some layers appear finely laminated, as if laid down in calm water over extended periods. In certain places, veins of light-colored minerals cross-cut older rocks, consistent with fluids moving through cracks and depositing materials as they cooled. These observations confirm that liquid water once altered and reshaped the Martian crust at the scale of individual outcrops as well as broad regions. Despite this rich record of past wet conditions, the planet of today is dry and cold. The atmosphere is thin, with a surface pressure so low that liquid water exposed on the ground would quickly boil and freeze. Temperatures often remain well below the freezing point of pure water, especially at night and in higher latitudes. Water now resides mostly as ice locked in polar caps and buried beneath the surface. Radar soundings from orbit reveal thick deposits of layered ice and dust, while fresh impact craters sometimes expose bright patches that fade as subsurface ice sublimates. In higher latitudes, polygons and patterned ground reminiscent of permafrost landscapes on Earth suggest that frozen water lies just beneath the soil. Near the equator, recurring dark streaks appear on steep slopes during warmer seasons and then fade, raising the possibility of small transient flows of salty water or of dry granular movements influenced by trace amounts of moisture. The precise mechanism behind these features remains debated. Some interpretations favor briny seeps that briefly flow before evaporating, while others point to dry dust avalanches or surface processes that do not require present-day liquid water. The air itself contains traces of water vapor and small amounts of other gases, including methane detected at low levels. Reports of variable methane concentrations changing with season or location have stirred interest because such molecules can arise from both geological and biological processes. On Earth, methane is produced by some forms of life, and also by serpentinization and other reactions involving rock and heat. On Mars, the origin and fate of the detected methane remain unclear. Some instruments see signals that vary over time, while others record little or none, creating tension between measurements and adding another layer of uncertainty. If methane is present and varying, it must be produced and removed on timescales that are surprisingly short in planetary terms, suggesting active processes still operating either in the subsurface or the atmosphere. The question of where the ancient waters went lies at the heart of Mars studies. To carve the observed valleys and fill the inferred lakes and possible oceans, large volumes of water and a denser, warmer atmosphere are required. One branch of evidence points to atmospheric escape. Measurements of isotopes in the current air show that lighter forms of elements such as hydrogen and argon have been preferentially lost, leaving behind heavier isotopes in higher relative amounts. Spacecraft that watch the upper atmosphere and its interaction with the solar wind record streams of ions being stripped away as charged particles from the sun sweep through the planet-extended exosphere. These findings support the idea that over billions of years the solar wind has eroded the Martian atmosphere, especially after the planet lost most of its global magnetic field. Magnetic data from orbit show patches of remnant magnetism locked into old crustal rocks, implying that early Mars once hosted a dynamo in its core that later shut down. Without a strong magnetic shield, the atmosphere became more exposed to energetic particles and escape rates rose, thinning the air and making stable surface water harder to maintain. Climate models attempt to reconstruct periods when volcanic outgassing greenhouse gases and possible clouds could have warmed the surface enough for water to flow, but reproducing conditions that allow sustained liquid water remains challenging. Some scenarios involve short, intense warming episodes triggered by large impacts or bursts of volcanic activity, leading to episodic lakes and rivers rather than continuous oceans. Others explore thicker atmospheres rich in carbon dioxide and additional greenhouse agents adjusted by changes in the young sun brightness. No single picture has yet captured all constraints, and each attempt leaves some observations only partially explained. Mars thus appears as a world caught between histories, its present desert state preserving clues of a wetter past while hinting at processes still unfolding. Dry channels and empty basins recall long vanished rivers and lakes. Buried ice, shifting dust, occasional gas detections, and the slow escape of atmosphere into space suggest that the planet is not entirely static but slowly evolving. In this quiet red landscape, the traces of lost rivers and missing air form a puzzle that connects the deep interior, the surface, the sky, and the space beyond, inviting further missions and models to piece together how a planet that once favored water became the cold, thin-aired world that circles the sun today. Between the orbits of Mars and Jupiter lies a broad region where many small bodies circle the sun, a zone known as the asteroid belt. From a distance, it might be imagined as crowded a dense ring of tumbling rocks, yet in reality, the belt is mostly empty space. Its objects are separated by wide distances, each following its own quiet path around the star. All drift in a shared neighborhood that marks the transition between the inner rocky worlds and the outer giants. This region sits close to where another full-size planet could have formed. The raw material was present in the early disk, but no single world emerged. Instead, there remains a dispersed collection of remnants, as though growth began and then stalled. One common thought is that the strong gravity of Jupiter continually stirs this zone-raising collision speed so that early planetesimals tend to shatter rather than merge. Another possibility is that one or more large bodies did form and were later disrupted, leaving a cloud of fragments that never again came together. Either way, the belt carries a sense of absence, a missing planet hinted at by the rubble it left or would have left behind. The orbits of many asteroids cluster into families that share similar paths and seem to come from common ancestors. Within these families, bodies often show related colors and compositions, suggesting that they are pieces of a parent object broken apart in a single event. Spectral measurements reveal a wide variety of surface types across the belt, from dark carbon-rich asteroids that swallow most of the sunlight that strikes them to brighter stony bodies and metallic fragments that may be the exposed cores of once larger worlds. Meteorites that fall to Earth provide matching samples. Some contain tiny, once molten droplets frozen into rock, recording brief bursts of heating in the early disk. Others show layered compositions that indicate melting separation of metal and silicate and slow cooling deep inside substantial parent bodies. By pairing meteorites with asteroid observations, researchers assemble a rough family tree of shattered worlds and half-formed planets glimpsed through the pieces that reach the ground. The distribution of orbits within the belt is not smooth. Certain distances from the Sun are nearly empty, forming gaps where objects are rare. These align with simple ratios between the time it takes an asteroid to orbit the Sun and the time needed by Jupiter. At these special distances, an asteroid repeatedly feels tugs from Jupiter at the same points in its path, gradually stretching and tilting its orbit until it is removed from the region. Some are pushed into more elongated trajectories that cross the paths of the inner planets, becoming near-Earth asteroids. Others are sent outward or even ejected from the solar system. The pattern of gaps and clusters acts like a fingerprint of Jupiter influence, showing how resonance has sculpted the belt over time. Models that follow the early movements of the giant planets suggest that Jupiter and Saturn may once have migrated from their birthplaces, disturbing wide regions of the young system. In such pictures, many asteroids would have been scattered, some driven inward to bombard the inner planets, others cast outward to join distant reservoirs. The present belt may therefore be only a thin remnant of a once more massive population, thinned and reshaped by the slow shifting of giant orbits. The asteroid belt also appears to have helped deliver material to the inner worlds. Some dark carbon-bearing bodies contain water, bound in minerals and simple organic compounds. When such objects strike early Earth, they can contribute extra volatiles and complex molecules to the surface, adding to supplies from comets and the original building blocks. In this way, the belt serves both as an unfinished planet nursery and as a reservoir feeding ingredients to places where life later arises. Spacecraft that have visited individual asteroids reveal surfaces that are at once familiar and strange. They show boulder-strewn plains, deep craters, and fractured cliffs that testify to repeated impacts, but they also point to low densities and fragile rubble pile structures held together more by gentle gravity than by solid strength. When a small asteroid spins too quickly, loose material can drift toward the equator and be shed into space, forming moons or thin rings of debris that circle the parent body in miniature versions of planetary systems. Subtle forces such as the uneven emission of heat from a rotating body warmed by the sun can slowly alter orbits and spin states, nudging objects into resonances where Jupiter and other planets then complete the process of scattering. These combined influences, weak on their own, but powerful over long times, keep the belt in slow motion, redistributing fragments without ever letting them settle into a single form. In the stillness between its scattered rocks and dwarf worlds, the asteroid belt holds many intertwined questions. Was there once a nearly finished planet here, later unmade, or did the presence of Jupiter always prevent such a body from forming? How many times have the orbits of the giant planets swept through and reset this structure To what extent do the meteorites that fall on Earth truly represent the diversity of objects that still circle in this zone? Each new mission and measurement adds a few more pieces to the picture, but the overall impression remains one of a missing chapter in planetary history written in fragments that drift between Mars and Jupiter like the quiet remains of possibilities the solar system almost but not quite realized. Jupiter moves along its wide orbit as a massive banded world far larger in diameter than Earth and more massive than all the other planets combined. From afar, it appears as a softly striped sphere, its clouds arranged in pale zones and darker belts that circle the globe, broken by ovals and storms that can linger for years. Beneath this atmosphere lies a deep gravitational well that quietly shapes the paths of smaller bodies. Asteroids, comets, and icy fragments feel its pull as they drift through the outer system or fall inward from distant reservoirs. Some are turned aside, some are captured into new orbits, and some are drawn into the giant itself. The layout of the inner worlds may also bear the imprint of this mass because during formation its growing gravity and any early migration could have stirred nearby material and altered the supply of rock and ice available closer to the Sun. The atmosphere of Jupiter consists mostly of hydrogen and helium with minor compounds that condense into cloud decks at different heights. In the upper layers, alternating eastward and westward, jets create bands that race around the planet, carving the familiar striped pattern. Where neighboring streams meet, turbulence forms. The Great Red Spot, a vast and enduring anticyclonic storm, rolls within this pattern as a high-pressure system larger than Earth surrounded by smaller vortices that merge, split, and fade. Observations over decades show that the spot slowly changes in size, color, and internal structure, so even this apparently permanent feature belongs to a fluid evolving system. Jupiter emits more energy than it receives from the Sun because heat left from its formation and slow contraction continues to leak outward. Rising plumes and sinking flows carry this energy through deep layers, driving lightning-filled clouds and auroras that flicker near the poles. Beneath the highest clouds, pressure increases until hydrogen behaves as a dense liquid. Deeper still, under greater compression, it enters a metallic state in which electrons move freely. Within this metallic hydrogen layer, motions of conducting fluid generate a powerful magnetic field. The resulting magnetosphere extends far into space, forming a large cavity in the solar wind and trapping charged particles in radiation belts around the planet. Material from the volcanic moon Io feeds this environment, creating a donut-shaped cloud of ions that co-rotates with the planet and leaves a signature in the auroras. Gravity measurements suggest that Jupiter also contains a central region enriched in heavier elements, perhaps a core that is partly dissolved into surrounding fluid. Whether this core began as a solid seed that gathered gas or arose through other pathways remains uncertain, and different models of its size and composition continue to be tested against the way the planet tugs on passing spacecraft. The gravitational influence of Jupiter reaches across the solar system. In the asteroid belt orbits, whose periods form simple ratios with Jupiter, are slowly destabilized, leaving gaps while other locations become quiet harbors. The Trojan asteroids occupy two such harbors that travel ahead of and behind Jupiter along its orbit. There, a three-way balance between the gravity of Jupiter, the gravity of the Sun, and the motion of the asteroids keeps them clustered in loose swarms. These bodies may preserve mixtures of rock and ice, little changed since early times, offering samples of material that never joined a full-sized planet. Farther out and farther in, countless small objects pass through regions where Jupiter pull either gently reshapes their orbits or flings them into new paths. Some simulations picture the young giant moving inward and then outward, scattering planetesimals toward both the inner and outer regions and perhaps contributing to an early surge of impacts on the terrestrial worlds. Comets from the Kuiper belt and the Oort cloud often pass near Jupiter as they fall toward the Sun. Some lose energy and become members of the Jupiter family, returning on short periods. Others gain energy and are ejected, set on trajectories that leave the solar system, while a fraction are deflected onto paths that cross the orbits of the inner planets. Over long spans of time, Jupiter acts as a filter, reducing the number of icy bodies that can repeatedly intersect Earth orbit, yet its perturbations also sometimes deliver new impactors into the inner regions. In the closing years of the 20th century, the comet Shoemaker-Levy 9, previously torn into fragments by tides, plunged into the atmosphere of Jupiter and left dark stains that persisted for weeks. Later brief flashes and temporary marks have revealed additional impacts by smaller bodies, reminders that large objects still move through the outer system and that Jupiter can intercept them. Orbiting Jupiter is a system of moons that resembles a miniature version of the solar system. The four large Galilean moons, Io, Europa, Ganymede, and Callisto, travel on their own paths, yet share resonances that keep some orbits slightly elongated. As they move around Jupiter, changing tides flex their interiors and generate heat. On Io, this heating drives intense volcanism and feeds clouds of gas into space. On Europa and probably Ganymede, tidal heat maintains global oceans of liquid water beneath shells of ice. Callisto, more distant and heavily cratered, seems colder and less altered, preserving an ancient landscape. Spacecraft that pass Jupiter or settle into orbit refine knowledge of this family of worlds, measuring gravity, magnetism, and cloud structure. Yet even with these data, Jupiter keeps many details concealed within thick clouds and fluid layers, standing in the outer sky as a calm banded disk whose gravity and moons quietly influence the evolution of the entire system. Saturn moves through its distant orbit as a pale flattened sphere wrapped in an immense system of rings that spread outward in a broad, thin sheet of ice and rock. From afar, the planet looks almost unreal, its bright rings forming a sharp, delicate outline that seems too precise to be natural. The main rings occupy a band only a few tens of meters thick in many places, yet they stretch across hundreds of thousands of kilometers from the planet. Viewed edge-on, they nearly disappear, a narrow line against the dark, but when they are more open, bands, gaps, and subtle gradients become visible, revealing a structure that is at once orderly and full of fine detail. For a long time, Saturn appears to be a model of quiet perfection, the rings seemingly eternal, but closer investigation shows a system that is restless, dynamic, and perhaps surprisingly young. The rings consist largely of water ice, from grains smaller than sand to blocks the size of boulders mixed with darker material that may be silicate dust or carbon-rich fragments. Sunlight scattered from these particles gives the brightest rings their nearly pure pale glow, while regions with more contamination appear grayer or slightly tinged. Spacecraft that pass through Saturn's system measure the mass of the ring material and find that despite its extent, the total amount is equivalent to only a modest-sized moon. Radio and stellar occultations, in which the rings block signals or starlight, reveal that density varies strongly, with radius forming sharp edges, narrow gaps, and spiral wave patterns that wind through the disk. Many of these features line up with resonances between ring particles and small moons orbiting outside or within gaps. At particular distances, the repeated tug of a moon injects energy into ring orbits, piling material into waves or clearing lanes. The result is a complex interplay in which moons sculpt rings and rings record the invisible rhythm of gravitational interactions. Cassini observations show tiny moonlets embedded in the outer rings, leaving propeller-shaped disturbances in their wake as they share angular momentum with nearby particles. These structures form, dissipate, and reform, indicating an ongoing process of aggregation and disruption at small scales. The atmosphere of Saturn itself is calmer in appearance than that of Jupiter, with broader, more muted bands and occasional storms that flare and then fade. Yet the interior also emits more heat than it receives from the Sun, and deep convective motions rise through hydrogen and helium layers, feeding weather systems that sometimes grow large enough to wrap around the entire planet. Close to the equator, a narrow band of fast winds circles the globe, while at the poles, curious patterns take shape, including a persistent hexagonal wave in the northern atmosphere. These atmospheric features do not directly form the rings, but the same planet-wide processes, rotation and gravity, that sculpt the atmosphere also control the environment in which the rings exist. Saturn, oblate shape flattened by its rapid spin, changes the precise way gravity falls off, with distance-modifying orbital resonances and the precession of ring particle paths. The rings therefore represent a thin cross-section of a wider gravitational and dynamical field that extends from the deep interior out to the outermost moons and beyond. Questions about the age and origin of the rings bring an element of unease to their beauty. If the rings formed together with Saturn from the original disk around the young Sun, they would have been bombarded for billions of years by micrometeorites and dust, gradually darkening the ice and grinding particles down. Some measurements of ring color and purity suggest that they are surprisingly clean, as though they have not endured such long exposure. Other lines of evidence point in different directions. Models of collisional evolution argue that a once more massive ring could lose much of its material over time through spiraling dust accretion into moons and bombardment, leaving a lighter, still bright system. One family of scenarios pictures a moon that strays too close to Saturn and is pulled apart by tidal forces, its fragments spreading into a ring that later evolves into the current pattern. Another suggests that repeated impacts onto an existing moon could strip icy layers and feed the rings, keeping them relatively fresh. Each version leaves certain observations only partially explained, and estimates of ring age range from a fraction of the life of the solar system to nearly its entire history. Cassini measurements deepen the mystery by revealing that the rings are actively losing material. Fine grains charged by sunlight and collisions feel both gravity and electromagnetic forces. Some spiral inward, forming a faint diffuse rain that falls along the planet magnetic field lines into its upper atmosphere. Spectral observations of Saturn indicate that non-native material is indeed entering the atmosphere at high latitudes, altering its composition. This ring rain implies that unless supplied by some balancing process, the rings will thin with time, eventually fading into a more subtle and sparse structure. The graceful arcs seen today may therefore represent a temporary state in a longer cycle, a phase in which enough material is present to form wide bright bands, but not so much that it rapidly clumps into new moons. If so, there is a quiet coincidence in the fact that observers happen to witness the rings during this luminous stage, somewhere between their violent creation and their slow dispersal. Saturn moons contribute further layers to this story. Enceladus, a small icy body within the orbit of many larger moons, vents plumes of water vapor and ice grains from fractures near its south pole. These jets feed material into a diffuse ring that shares its orbit. The particles that escape Enceladus add to the larger ensemble of rings and are in turn shaped by gravity collisions and sunlight. Titan, Saturn's largest moon, follows a more distant path but exerts subtle tugs on inner moons and may have influenced the distribution of material during the system's early evolution. Other small moons within or near the rings act as shepherds, their gravity collecting particles along narrow edges or maintaining thin ringlets inside gaps. Where a moonlet's orbit crosses the ring plane, it can open a lane, gather an arc, or cast out wakes, leaving transient patterns that drift and blur. In this way, the rings and moons form a coupled system in which mass, angular momentum, and energy move back and forth, slowly rearranging both over timescales far beyond human experience. Taken together, the observations portray Saturn rings as neither static decoration nor simple debris, but as an active, evolving disk whose graceful appearance hides rapid collisions, constant sculpting by resonances and steady loss of material. Their changing brightness and structure encode information about how icy bodies fracture, how tides tear and rebuild, and how gravity shapes thin disks around massive planets and perhaps around young stars. Whether these rings are ancient survivors wearing the marks of long weathering or youthful structures born from more recent disruption remains unsettled. For now they hang like a luminous, fragile frame around Saturn, a broad, nearly flat world of ice and shadow that seems calm from a distance, yet proves on closer inspection to be only a passing arrangement in a longer, quieter sequence of formation and decay. Far from the warmth of the inner planets, several moons circle the giant worlds as small, bright spheres of ice and rock. At first glance, they seem cold and inert, glinting in reflected sunlight as they move along their orbits. Yet beneath their frozen shells, hidden from direct view, evidence points to deep, dark oceans of liquid water, warmed not by starlight, but by the constant kneading of tidal forces. Among these worlds, Europa around Jupiter and Enceladus around Saturn stand out as particularly compelling, each offering a different window into the quiet possibility of habitable environments in places where no one first expected to find them. Europa travels close to Jupiter, locked in a resonance with two of its sibling moons that ensures its orbit remains slightly elongated rather than perfectly circular. As Europa moves along this path, the immense gravity of Jupiter flexes the moon inward and outward, generating internal friction and heat. The surface of Europa is a smooth, bright shell of water ice marked by a network of long intersecting ridges and fractures. Impact craters are relatively scarce, suggesting that the crust is geologically young and has been repeatedly renewed. In some regions, blocks of ice appear to have broken, shifted, and refrozen, forming jumbled terrains that look like frozen seas, pushed and tilted by internal motion. Magnetic measurements taken near Europa show a fluctuating signature that is difficult to explain with a purely solid interior. The most straightforward interpretation is that a global electrically conducting layer lies beneath the ice, most likely a deep ocean of salty liquid water. Models of Europa interior structure place this ocean between a rocky mantle below and an icy shell above, with thicknesses that remain uncertain but could allow an ocean tens of kilometers deep wrapped entirely around the moon. The presence of salt would not only improve electrical conductivity, but also lower the freezing point, making it easier for the ocean to remain liquid under the combined effects of tidal heating and insulation. Additional clues come from observations of faint plumes of water vapor and fine ice grains that appear to erupt from Europa's surface in certain regions. These plumes are intermittent and delicate, but when present, they suggest that fractures in the ice crust can tap reservoirs of liquid or slushy material at depth and vent it into space. If such vents are confirmed and better characterized, they would provide a rare opportunity to sample subsurface material without drilling, as future spacecraft could fly through the ejected particles and analyze their composition directly. The chemistry of any organic molecules, salts, and gases in these grains would offer hints about the conditions within the hidden ocean and the possible presence of chemical gradients that might support life. Enceladus presents a parallel yet distinct case. Much smaller than Europa and circling Saturn rather than Jupiter, it orbits within one of Saturn's thinner rings. Its surface is a patchwork of bright ice, heavily cratered in some areas and remarkably smooth in others. Near its south pole, a set of long fractures, often called tiger stripes, cross the terrain. From these fissures, plumes of water vapor, ice grains, and organic compounds jet into space in a continuous or near continuous spray. Spacecraft that have passed through these plumes have sampled the material, detecting salts, simple organic molecules, and tiny silica particles that likely form in hot water interacting with rock. These findings indicate that Enceladus hosts a subsurface ocean beneath its ice shell, at least in the southern hemisphere and possibly extending globally. The presence of silica grains of specific sizes suggests that water in contact with the rocky core has been heated to temperatures compatible with hydrothermal activity, where minerals dissolve and later precipitate as conditions change. This picture resembles in some ways hydrothermal vent systems on the floor of Earth oceans, where hot mineral-rich water rises from the crust and creates steep chemical gradients. On Earth, such environments support rich ecosystems independent of sunlight, drawing energy instead from chemical reactions between rock and water. On Enceladus, no direct evidence of life has been found, yet the combination of liquid water, warmth, and reactive chemistry underscores its status as a potentially habitable niche in the outer solar system. Other icy moons add layers to this emerging pattern. Ganymede, the largest moon in the solar system, appears to host a deep layered interior with multiple sheets of ice and possible oceans stacked above a rocky core. Its strong internal magnetic field, unique among moons, suggests a partially liquid interior where electrically conducting fluid moves and sustains a dynamo. Callisto, more distant and heavily cratered, may also carry a buried ocean, inferred from how it responds to changing magnetic fields. Around Saturn, Titan hides its surface beneath a thick nitrogen-rich atmosphere and possesses lakes and seas of liquid hydrocarbons on its surface, while also likely containing a water ocean at depth. Even smaller bodies such as Dione and possibly others show hints of subsurface liquids from gravity and topography data. The mechanisms that maintain these oceans vary but share common themes. Tidal forces flex the moons as they travel in slightly eccentric orbits, converting orbital energy into heat that can keep water from freezing solid. In some cases, radioactive decay in the rocky interior adds to the heat budget. The thickness of the ice shell, the presence of salts and ammonia, and the efficiency of heat transport determine whether an ocean can persist for billions of years or only for shorter intervals. The fact that several moons seem to have maintained liquid layers across long spans of time suggests that such environments may not be rare in planetary systems even far from the central star. The existence of oceans in the dark raises questions that reach beyond the details of any one moon. If life can arise or persist in such settings, relying on chemical energy at seafloor vents rather than sunlight at the surface, then the range of potentially habitable worlds expands greatly. Even in the absence of life, the chemistry occurring in these hidden seas may be complex, producing organic compounds and intricate mineral structures that record the interplay between rock, water, and energy. Future missions designed to orbit or land on these moons, to sample plumes, or perhaps one day touch the ice near active fractures, aim to read this record with greater clarity. For now, the picture remains incomplete. The thickness of the ice above Europa Ocean, the true extent of Enceladus Sea, the longevity of Ganymede interior layers, and the details of circulation within these hidden waters are only partly constrained by current data. Each measurement narrows the possibilities, but leaves room for multiple models, and small differences in assumed composition or heat flow can lead to very different interior structures. These uncertainties preserve a sense of mystery around the icy moons, holding open a quiet question about how common deep oceans might be and what they might contain. In the dim reaches around Jupiter and Saturn, where sunlight is weak and surfaces are frozen, these concealed seas remain among the most intriguing places in the solar system, combining the familiarity of water with the strangeness of permanent night, and standing as patient, silent worlds that may yet reveal whether life can flourish in the dark. Uranus circles the Sun at a great distance, a pale bluish world that at first glance seems quiet and unremarkable. Its disk appears smooth and nearly featureless in visible light, with only faint bands and occasional clouds. Yet one fact about Uranus stands out immediately. The planet is tipped almost onto its side. Its spin axis lies close to the plane of its orbit, so that it rolls along like a turning barrel rather than spinning upright. This extreme tilt close to a right angle relative to its path around the Sun gives Uranus seasons that are unlike those of any other planet. For long stretches, one pole points almost directly toward the Sun, while the other sinks into extended darkness. A single season at a pole can last for many Earth years, with the Sun circling low over the horizon or not rising at all. In between these extremes, the equatorial regions experience more nearly usual day and night cycles, but the overall pattern of heating and cooling across the globe is deeply altered by this geometry. The origin of such a tilt is not fully known. A leading idea is that during the early years of the solar system, when large collisions were still common, Uranus was struck by one or more massive bodies. A glancing off-center impact by a protoplanet could have tipped the spinning planet over, reorienting its axis while leaving its orbit largely unchanged. Another possibility considers a slower, more drawn-out process in which the combined gravitational pulls of other giant planets and the mass of a large system of satellites gradually shifted the axis over time. Each scenario leaves particular imprints on the internal structure and the arrangement of moons and rings. Measurements to date favor a violent early event, but the details remain open, and the true sequence of impacts and adjustments that produce the present tilt is still being explored through models in comparison with observations. Around Uranus lies a system of narrow rings and small moons arranged in a plane that is itself tipped along with the planet. The rings are far darker than those of Saturn, composed of material that reflects little light and is likely rich in carbon and rock as well as ice. They were discovered when they briefly dimmed the light of background stars, revealing their presence as thin, opaque strands circling above the planet cloud tops. The moons, ranging from modest irregular bodies to larger rounded worlds, show a variety of terrains, including canyons, faulted surfaces, and signs of past internal activity. Some display patterns that suggest cryovolcanism, in which water or other volatiles once flowed like lava across icy crusts. The tilted geometry means that as Uranus moves along its long orbit, the viewing angle of the rings and moons from the Sun slowly changes. There are times when the rings are seen edge on from Earth and nearly vanish from view, and times when they open wide and display their full structure. For the moons, sunlight can alternately favor one hemisphere and then the other over long seasons, giving each face extended periods of light or darkness. The atmosphere of Uranus consists mostly of hydrogen and helium, with a notable amount of methane, which absorbs red light and gives the planet its soft blue hue. Compared with Jupiter and Saturn, Uranus shows relatively subtle cloud features and a more muted pattern of bands and storms, at least in the wavelengths where it has been most often observed. Winds still blow at high speeds and deeper layers may host more complex flows, but the visible appearance suggests a calmer, more uniform outer layer. One of the persistent puzzles about Uranus concerns its internal heat. While other giant planets radiate significantly more energy than they receive from the Sun, Uranus seems unusually faint, emitting only a little more than the absorbed sunlight, or perhaps roughly the same. This low level of intrinsic heat hints that something in its history or structure has restricted the escape of energy. Some explanations point again to a major early impact that might have disrupted the internal layering and left heavy elements unevenly mixed, suppressing convection and trapping heat. Others examine whether a stable stratification formed naturally as the planet cooled, creating layers that do not easily exchange material. The lack of a clear answer keeps Uranus as a key target for future missions that could probe its gravity-magnetic field and atmospheric composition more thoroughly. Neptune, orbiting even farther out, shares many characteristics with Uranus and is often grouped with it as an ice giant. It has a similar overall composition with a larger fraction of water, ammonia, and other volatiles in its interior than Jupiter or Saturn, and a visually comparable blue tone due to methane in its upper atmosphere. However, Neptune appears more active with visible storms and higher atmospheric winds despite receiving less sunlight. Large dark spots have been seen drifting across its cloud tops, accompanied by bright companion clouds thought to form as air forced upward condenses into crystals. Neptune radiates more than twice the energy it receives from the Sun, indicating a stronger internal heat source. Why two planets of similar size and makeup show such different energy balances and atmospheric behaviors is not yet fully clear. Their internal structures, rotation rates, and histories of cooling and mixing may differ in subtle but important ways. Comparisons between Uranus and Neptune therefore act as a natural experiment, highlighting how variations in formation and early evolution can produce significantly different outcomes among broadly similar worlds. Both Uranus and Neptune possess magnetic fields that are markedly unusual. Instead of being roughly aligned with their spin axes and centered on the planets, their magnetic fields are tilted at large angles and offset from the centers. The result is that regions of strong magnetic influence dip and sweep in complex patterns as the planets rotate, producing rapidly changing environments in their magnetospheres. This geometry suggests that the regions where the magnetic fields are generated lie in shells or layers closer to the outer parts of the interior, rather than in deep central metallic cores, as is thought to be the case for Jupiter and Saturn. Conducting fluids rich in water and other volatiles compressed into exotic phases under high pressure may host swirling motions that sustain these odd dynamos. Laboratory experiments and theoretical studies of such materials under extreme conditions remain challenging, so the magnetic fields of Uranus and Neptune provide some of the few direct clues to the behavior of matter in these regimes. The orbits of Uranus and Neptune themselves also hold quiet hints about the broader history of the solar system. Models of planet formation and migration often show that the giant planets did not always occupy their present positions. Interactions with the surrounding disk of planetesimals can cause their orbits to shift inward or outward, sometimes crossing resonances that lead to rapid rearrangements. In several such scenarios, Uranus and Neptune trade places or move outward significantly, scattering large numbers of icy bodies and reshaping the distribution of material in the distant regions. These migrations help explain the current structure of the Kuiper Belt and the existence of certain resonant populations of objects beyond Neptune. The present locations and eccentricities of the ice giants thus encapsulate past journeys that are not directly visible journeys that have left their clearest signs in the outer debris. Uranus, with its sideways spin, faint heat, and tilted magnetic field, and Neptune with its energetic storms and distant drifting path, stand together as markers of a complex past. They remind observers that even in the dim outskirts of the solar system, beneath apparently smooth blue atmospheres, the traces of deep collisions, slow migrations, and unfamiliar interior physics continue to lie hidden, awaiting closer inspection. Beyond the orbit of Neptune stretches a broad and faint region known as the Kuiper Belt, a ring of icy bodies that circles the sun in deep cold. Here sunlight arrives as a weak glow, and the objects that reflect it are small. From Earth, even the largest of these worlds appear only as slowly shifting points of light, yet as more are found, a picture emerges of an outskirts that is not random but quietly structured. The Kuiper Belt contains dwarf planets, smaller icy worlds, and countless fragments that never joined into full-sized planets. Pluto moves within this realm on an elongated tilted path that sometimes brings it closer to the Sun than Neptune. Its orbit is locked in a resonance with Neptune, completing 2 circuits of the Sun for every 3 completed by the larger planet. This repeating pattern ensures that their orbits do not lead to close approaches, even though their projected paths appear to cross. Many other Kuiper Belt objects occupy similar resonant relationships, their positions set by regular gravitational nudges that either stabilize or gently shift their motion. Between these resonant families, other bodies travel on more scattered routes. Some remain near the average plane of the solar system, while others follow orbits that are steeply inclined. A few occupy extraordinarily elongated paths that carry them from the outer belt to regions far beyond, taking many millions of years to complete a single loop. Several of these distant orbits seem to share certain alignments, as if some unseen influence had drawn their closest approaches into similar directions in space. The idea that this pattern is more than chance has led to proposals of a hidden planet, perhaps several times the mass of Earth, moving on a remote and tilted orbit. In models that include such a world, its slow gravity gradually raises and twists the orbits of small bodies over tens of millions of years, grouping their closest approaches in orbital tilts. Simulations can reproduce some of the observed clustering when the unseen planet is placed far from the Sun. Yet the sample of known distant objects remains small and observational biases are strong. Telescopes search more deeply in some directions than in others. Until many more extreme Kuiper Belt and inner Oort cloud objects are mapped, the case for a hidden planet remains an open possibility rather than a confirmed presence. Even without invoking extra planets, the Kuiper Belt itself records a history of motion. The sizes and orbits of its bodies point toward a time when the giant planets did not sit where they do now. In several families of models, Neptune migrates outward through a disk of icy planetesimals, capturing some into resonances and scattering others onto higher inclination and more distant paths. Many bodies are ejected entirely, seeding a remote spherical cloud of comets. The present belt then appears as a surviving inner rind of a population that was once more massive, trimmed and reshaped by the wanderings of the giant planets. A single spacecraft flyby has given a close look at this distant zone. After passing Pluto and its moon Charon, one mission turned toward a smaller Kuiper Belt object, revealing a contact binary shaped like 2 lobes gently fused together. Its lightly cratered surface suggests a body that has changed little since early times. Such objects preserve mixtures of ice and dark organic material that were laid down in the outer protoplanetary disk and altered only slowly by cosmic rays and faint sunlight, frozen samples of the raw ingredients from which the outer planets and their moons were assembled. within the belt collisions still occur, though at very low rates. When they do, they can create families of fragments that share similar orbits and surface properties. By grouping bodies with matching colors and orbital shapes, researchers can identify these families and work backward to infer the nature of their vanished parents. Some parent bodies seem to have been relatively bright and icy, others darker and richer in complex carbon compounds. This diversity suggests that even within the same general region of the disk, conditions during formation varied enough to leave distinct chemical signatures that have lasted for billions of years. Farther out beyond the main concentration of Kuiper belt objects lie scattered and detached bodies whose orbits blur the line between the belt and the inner Oort cloud. Here, the plane of the solar system matters less, and paths can be steeply inclined or nearly random. The modest number of such known objects carries disproportionate weight in attempts to reconstruct the architecture of the far solar system. Each newly discovered orbit refines or reshapes the picture, supporting or weakening the notion of hidden perturbers and shifting estimates of how far the sun influence truly reaches. For now, the Kuiper belt remains a region of shadows and wandering paths, its inhabitants faint, cold, and slow-moving. Their orbits trace a quiet record of migrations, encounters, and erosive collisions that began when the solar system was young and continue at a gentler pace today. The belt marks a soft boundary beyond which the organized family of planets gives way to a more diffuse halo of icy fragments. Comets perturbed inward from this zone carry the chemical fingerprints of primordial ices toward the inner system. Those scattered outward join the deep reservoir that surrounds the solar system as a distant invisible cloud. In this way, the Kuiper belt serves both as an archive and as a gateway, its subtle alignments and gaps hinting that the full inventory of bodies and forces in this dim frontier has not yet been completely revealed. Far from the bright inner system, the influence of the sun stretches outward in a vast invisible bubble called the heliosphere. Within this region, charged particles streaming from the sun, the solar wind flow outward in all directions, carrying the solar magnetic field with them. For most of the planets, this wind forms a steady, though variable background, a thin plasma that shapes magnetospheres and tails. But at great distances where the density of the solar wind falls and the pressure of the surrounding interstellar gas becomes comparable, a boundary begins to form. This boundary is not a sharp wall, but a layered transition where the character of space quietly changes from solar to galactic. Close to the sun, the solar wind moves at supersonic speeds relative to the thin gas ahead. Eventually it slows as it encounters resistance. At a certain distance, the flow drops below the speed at which pressure waves can travel through the plasma, forming a surface known as the termination shock. Beyond this shock lies the heliosheath, a region where the wind is compressed, heated, and deflected as it adjusts to the presence of the interstellar medium. Farther out still at the outer edge of the heliosheath resides the heliopause, the approximate boundary where pressure from the solar wind balances the opposing pressure of the local interstellar gas and magnetic field. This is often described as the edge of the solar system in terms of the sun-direct particle influence, even though gravity and comets extend much farther. Two spacecraft launched by the National Aeronautics and Space Administration in the late 1970s provide the first direct crossings of this distant frontier. Voyager 1 and Voyager 2 travel outward on long, curving paths that carry them past the giant planets and then into the deep outer regions. As they move away from the sun, their instruments register changes in particle fluxes, magnetic field direction, and plasma density. Voyager 1 encounters the termination shock at a distance of many billions of kilometers. then later passes through the heliopause into a region where particles from outside the heliosphere dominate. The energy and direction of cosmic rays, high-energy particles arriving from the galaxy, change sharply at this crossing, signaling that the spacecraft has entered interstellar space. Voyager 2 follows a different route and crosses the same boundaries at somewhat different distances, revealing that the heliosphere is not a perfect sphere, but is shaped and distorted by the surrounding interstellar conditions and by the varying solar cycle. Within the heliosphere, the solar wind helps shield the inner system from a portion of the galactic cosmic rays, deflecting or slowing some of them. When solar activity rises, the strengthened wind and magnetic field push the edge of the heliosphere outward and increase the shielding, reducing the number of high-energy particles that reach the inner planets. When activity falls, the boundary may contract slightly and the shielding weakens. Over long times, these subtle changes can influence radiation levels and perhaps even chemical processes in planetary atmospheres, though the exact links remain carefully studied and not fully settled. Outside the heliopause, the density of the interstellar plasma is higher and the magnetic field lines follow the larger structure of the galaxy. The region where the sun motion through this medium creates a compressed front or wake is still being mapped indirectly through observations of neutral atoms and distant emissions, leaving some debate about whether a bow shock, a bow wave, or a more complex structure forms ahead of the moving heliosphere. The picture becomes more intricate when considering that the local interstellar medium itself is not uniform. The sun currently travels through a relatively warm, low-density cloud of gas and dust, but in the distant past and future, it may have passed or may yet pass through denser or more rarefied regions. Each change in environment would alter the size and shape of the heliosphere, strengthening or weakening the shield it provides. Sedimentary and isotopic records on Earth have been examined for hints that such passages might correlate with variations in cosmic ray flux and in turn with subtle climate shifts, but the connections are difficult to prove conclusively. The idea that the large-scale journey of the solar system through the galaxy might leave a faint imprint on planetary surfaces and atmospheres adds another layer of quiet complexity to the story of this boundary. Beyond the heliosphere lies the domain of the Oort cloud, a vast hypothetical shell of icy bodies that extends far beyond the Kuiper belt. Individual objects in this cloud are too distant and faint to be seen directly, yet their existence is inferred from the orbits of long-period comets that arrive from almost random directions. These comets seem to come from a roughly spherical reservoir surrounding the Sun at distances tens of thousands of times greater than that of Earth orbit. Perturbations by passing stars, galactic tides, or perhaps unseen structures in the local interstellar medium can gently dislodge some of these bodies, sending them drifting inward over millions of years until they fall into the inner system as bright visitors. In this way, the gravitational reach of the Sun extends far beyond the heliopause, even though its direct particle influence fades. The edge of the solar system therefore depends on what aspect is considered the limit of the solar wind, the range of significant gravity, or the last loosely bound comet. None of these boundaries is perfectly sharp, and each shifts slowly with time. In the far future, the Sun itself will change. Over billions of years, it brightens and then evolves off the main sequence, expanding into a red giant and altering the conditions throughout the system. Inner planets may be engulfed or stripped, outer regions warmed and distant ices stirred. The heliosphere will grow and shrink in response to changing solar winds, and eventually, when nuclear fusion in the core ceases, the Sun will shed its outer layers and contract into a white dwarf. The solar system will enter a new phase in which planets, asteroids, and comets orbit a faint, dense remnant star surrounded by a slowly thinning shell of gas. Many details of this distant evolution remain model-based, and the exact fate of specific worlds is uncertain, but the overall trajectory points toward gradual dimming rather than sudden disappearance. The measurements from Boundary Crossing probes the modeling of shifting heliospheric shapes, and the distant prospect of stellar aging together suggests that the solar system is not a closed static bubble, but a moving, changing structure embedded in a much larger environment. It drifts through the galaxy, trades particles and radiation with interstellar space, and responds to both internal cycles and external tides. At its outer edges, the sun softens into the glow of a local star among many, and the security of its protective wind gives way to the more ancient background of galactic cosmic rays. Yet even in this vast context, the delicate arrangement of planets, belts, clouds, and boundaries around this single star retains its identity, a quietly evolving system whose outer limits are still being traced step by patient, step by small machines that continue their slow flight into the dark.